Welcome to Lecture 5 of How to Read and Do Proofs. So, in our last lecture, we learned about the existential quantifier there is, there are, there exists. And when you see these keywords in the forward process, you know that there is an object with a certain property such that something happens. And all you have to do is use that object with its properties and work forward. On the other hand, when you see those keywords in the backward process, now it's your job to show that there is an object with a certain property such that something happens. Anybody remember the proof technique for doing that?
The construction method?
The construction method, that's right. And with the construction method, what you have to do is you have to go out and produce the object. Guess it, devise an algorithm to produce it. We don't really care how you produce it, but you have to create it. And of course, that is a creative process. And the guidelines that I can give you there are to turn to the forward process, use the information in the hypothesis to create the object, or you can look at the properties that you want the object to satisfy and play with those properties to try and construct the object. In any case, please remember that constructing the object by itself does not constitute the proof. What you have to do is show that the object you constructed is the correct one. What do we mean by the correct one?
It satisfies the conditions?
It satisfies all the conditions, the certain property and the something that happens. Okay, any questions about the construction method? Okay, so today what we're going to do is we're going to look at the universal quantifier for all, for each, for any, and for every. Let's look at this example. For every real number x greater than 0, 2 to the x is greater than 1. When you see these keywords in different branches of mathematics, you can always write these statements in a standard form, and that standard form looks like this. For every object with a certain property, something happens. And just like with the existential quantifier, it's your job to be able to identify the objects, the certain property, and the something that happens. Let's take this example. For every real number x strictly positive, 2 to the x is bigger than 1. What's the object here?
Real numbers x.
Real numbers x, exactly. And what's the certain property?
2 to the x greater than 1.
Nope. 2 to the x greater than 1, that is not the certain property. X is greater than 0, right? For every object with a certain property, something happens. As with the existential quantifier, when you identify the object, be sure to specify its type. In this case, a real number x, could be a function, could belong to some set. Identify the type of object. Also, some of these items in the statement can be either implied from the context, missing altogether, or even out of order, as you're going to see in just a moment. Let's take a couple of examples to practice this. So here's an example. For every angle t, sine squared of t plus cosine squared of t is 1. What's the object here?
Angle t.
Angle t, which is really a real number, right? Because whether you express it in radians or you express it in degrees, it's really a real number. What's the certain property?
Nothing.
Nothing, exactly. There is none. And the something that happens?
Sine squared t plus cosine squared t is equal to 1?
Correct. Just as the quantifier there is written with a backward e, so mathematicians use the symbol upside down a for the words for all. For example, for all real numbers y greater than 0, there is a real number x such that 2 to the x equals y. What are the objects here?
Real numbers y?
Real numbers y, the certain property.
Greater than 0.
Greater than 0, and the something that happens.
There is a real number.
Yes, everything after the certain property. There is a real number x such that 2 to the x equals y. Good. In some cases, the authors will write the for all after the something that happens. Here's an example. 2 to the n is greater than n squared for all n equal to 5, 6, and so on. What are the objects here?
2 to the n greater than n squared.
2 to the n greater than n squared. No.
Just n.
Just n, exactly. And what kind of an object is n?
Real number, an integer?
Ah, you see the difference? You were going to say real number, but in fact it's an integer. It's implied from the context here in which it's used. So this is where you need to be careful to identify the object and what kind it is. It's an integer. What's the certain property? N equal 5, 6, 7, 8, and so on. In other words, n bigger than or equal to 5. And what's the something that happens?
2 to the n is bigger than n squared?
2 to the n is bigger than n squared. Notice how it's out of order. Notice how sometimes the type of object is implied. This is typical with the way mathematics is sometimes written. So also, you need to watch out for hidden quantifiers where the keyword for all doesn't appear explicitly, as in the statement, all angles t between 0 and pi over 4 satisfy sine of t bigger than cosine of t. So one of the areas in which the keywords for all, for each, for any, for every arise is in the context of working with sets. So I hope you are comfortable with set notation. This is the set of elements 1, 4, and 7 listed here, enclosed in braces. And sometimes we use what is called set builder notation to describe the set. The set of real numbers x such that x is non-negative. It is usually the case that you can write a set in different ways. So for example, here's a set S, the set of real numbers x such that x squared minus x plus 2 is less than or equal to 0. Here's another set, T, the set of real numbers x such that x is between 1 and 2. It turns out that these two sets are exactly the same. So what do you think we mean by two sets being the same? The numbers inside the sets need to be exactly the same. That is, all the elements that you see in the set S should be in the set T, and vice versa. All the elements that are in the set T should be in the set S. So that gives us a definition, and here it is. A set S is a subset of a set T, written S subset of T, if and only if for every element x belonging to the set S, x is also in T. And here you see those keywords for every, the universal quantifier. All right, so for this, for every statement, let's identify the objects, the certain property, and the something that happens. So what are the objects here? Elements x in the set S. That's the object. And again, this is why you need to describe the type of object. It's an element in the set S. That's the type of object. What's the certain property?
There is none.
There is none, that's right. And the something that happens?
X is an element in T.
X is an element in T. So now we can define what it means for two sets to be equal. A set S is equal to a set T if and only if S is a subset of T, meaning all the elements that are in S are in T, and T is a subset of S, meaning all the elements that are in T are also in S. So using these definitions now, what we're going to do is talk about proof techniques. The keywords for all, like any keywords, can appear either in the forward process or in the backward process. And so we have two different proof techniques. When you see the keywords for all in the forward process, you're going to use one proof technique. When you see the keywords for all in the backward process, you're going to use a different technique. So today's lecture is about the backward process. So when you see the keywords for all in the backward process, what you want to say to yourself is, you have to show that for every object with a certain property, something happens. You have to convince yourself or someone else that for every object with a certain property, something happens. So how can we do that? Well, so let me make a suggestion for an approach here. Let's make a list of every object with a certain property. So here we go. Here's x1. That's an object with a certain property. Here's another object, x2, with a certain property. Let's make a complete list of all the objects with a certain property. Now look at the statement B. How can you convince somebody that for every object with a certain property, something happens? What do you have to do to this list? For each object on the list, what do you have to do?
See if the something happens.
Show that the something happens. Exactly. For every element on that list, you have to show that the something happens. So for x1, you have to show that something happens. For x2, you have to show that something happens. For all of these, you have to show that the something happens. Now, if the list only has 1 or 2 or 3 items on it, this will be a reasonable approach. But I'm sure you can appreciate that if this list is long or even infinite, this is not practical. You cannot show that the something happens for every object on the list. Do not do this for homework. It will take you a long time. The choose method is a proof technique for overcoming this difficulty. And let me explain how it works. So to understand the idea of the choose method, let's take that first item on the list, x1. That's an object with a certain property. And let's say that we create a proof to show that for that object x1, indeed the something happens. So we do some kind of proof that might read something like this. Because x1 satisfies the certain property, it follows that this happens, and then this happens, and therefore this happens. And finally, x1, for x1, the something happens. So we've done this proof for x1. Now, imagine that this proof has a very special property. Imagine that everywhere you see x1 in this proof, you can replace it with x2, and the proof still works. So, if that were true, would you make me show you that the something happens for x2 all over again? Couldn't I just say to you, hey, take this proof that I just did, and everywhere you see an x1, put in an x2? Wouldn't that be okay? So I wouldn't actually have to redo the proof for x2. I could reuse my proof for x1. Well, wouldn't it be nice if I could reuse that same proof, not just for x1, not just for x2, but in fact for any of those objects with a certain property on the list? Then I would only have to do this one proof. And that's the idea of the choose method. The idea of the choose method is to create a single, let me call it a model proof. And here's how the model proof is going to have to work. You can assume that x is a, let me call it a general object with a certain property. And in this proof, what do you have to show about that object?
Something happens.
The something happens, exactly. So we're going to create one model proof in which we have an assumption that x is a general object with a certain property, and we're going to use that to create the proof and show that the something happens. And then the idea is that once you've created that model proof, you can just reuse it for all the objects on the list. You don't have to actually do it yourself. Pretty clever, these mathematicians. To summarize, with the choose method, here's what you want to do. You want to choose a general object, let's call it x, with the certain property. And when you choose this object with the certain property, that becomes forward information. This is a new statement in the forward process because you chose the object x with the certain property. Here it is. I can use this object with its certain property. And you have to show that for that object x, the something happens. And that becomes a new backward statement. This is what you have to show. So now what we hope to do is fill in the details, probably by the forward-backward method, for example, to complete the model proof, working forward from A1 and backward from B1. And that becomes our model proof. For example, to show that for all real numbers x with x squared minus 3x plus 2 less than or equal to 0, x is between 1 and 2. Let's take a look at this for all statement. What are the objects? Real numbers x. What's the certain property? X squared minus 3x plus 2 is less than or equal to 0. And the something that happens? Now let's look at how the choose method works. Because I see the keywords for all in the backward process, this is when you want to think about using the choose method. And how does the choose method work? You choose an object with a certain property. So what should I choose here? A real number y, again, with the certain property. Now, some authors will use the same letter or the same symbol for the chosen object, but they're really different. So let me urge you to be careful with notation. This x up here is a general for all x, for all real numbers x. This symbol down here, in this case y, is a specific chosen one. So again, watch out for this overlapping notation. It's very common with mathematicians. They might use the same symbol x for the chosen object as for the general object, but these two are not the same. So choose an object, or in this case a real number y, with a certain property. What do we have to show for this chosen object?
That it is between 1 and 2.
That y is between 1 and 2, and that becomes our new backward statement. So now create the model proof and complete the choose method by working forward from A1 and backward from B1. So let's actually do this in the context of a mathematical proof. So here's a proposition that we want to prove. If S and T are sets defined by, S is the set of real numbers x such that x squared minus 3x plus 2 is less than or equal to 0, and T is the set defined by the set of real numbers x such that x is between 1 and 2, then S equals T. Of course, you've identified the hypothesis A and the conclusion B. Now, the next thing I urge you to do is to consciously choose a proof technique based, in essence, on keywords. So what keywords do we know? There is for all. We will learn more, but right now those are what you look for. So look at the hypothesis A and the conclusion B. Do you see any keywords?
No.
No, not written out there. That's right. So that means when you don't see keywords, what proof technique should we use to get started?
The forward-backward method?
The forward-backward method. That's right. So in this case, we're going to start with the forward-backward method because we don't see any keywords. And so let's work backward from the conclusion here. You know what I'm going to ask? What is the key question? How can I show that
Two numbers are equal.
two numbers are equal? No, S and T are not numbers.
Sets.
Right. How can I show that two sets are equal? Good. Everybody okay with the key question? How can I show that two sets, namely S and T, are equal? Well, after you ask the question, you got to answer it. How can you show that two sets are equal?
One contains the other, and the other contains the first.
Yes, the first is a subset of the second, and the second is a subset of first. Where did that answer come from? Definition. Again, remember, we use definitions all the time. So using the definition to answer that key question, here's our new statement in the backward process. All right, so now we have two things to show here. S is a subset of T, and T is a subset of S. Let's do the first one. Let's start by showing S is a subset of T, and later we'll come back and show that T is a subset of S. So let's just focus here on this one. Let's work backward from here by asking a key question. How can I show that?
A set is a subset of another set.
Excellent. A set is a subset of another set. Exactly right. And how can you show a set is a subset of another set? The definition says that you must show that all the elements that are in S are also in T. So here's the new statement B2 that I hope you would be able to write down. You have to show that for every element X in the set S, X is in T. Now what? Look at the statement B2. What do you notice?
For all.
The keywords for all in the backward process. And this is, again, the trigger that should say to you, now is the time to think about using the choose method. Everybody see how this is working? All right, so now you got to remember how the choose method works. So first of all, let's identify the objects, the certain property, and the something that happens in B2. What are the objects? Element X in S, that's the object. What's the certain property? There is none. And the something that happens? X is an element of T. Okay, for every object with a certain property, something happens. Now you have to remember how the choose method works. And the answer is you have to choose an object with the certain property. So what should I choose here? Choose an element X in S. And notice again, overlapping notation. Be careful here. This is a general for all X. This is a specific chosen X. How does the choose method work? You choose an object with a certain property for which you must show that X is an element of T, and that becomes your new backward statement. And now we have to complete this proof. Work forward from A1 and backward from B3. So let's work backward from B3. What's the key question? How can I show that an element is in a set? Exactly. How do you show an element is in a set? If it satisfies the defining property of the set. What's the key question for B3? How can I show that an element belongs to a set, for which an appropriate answer is I have to show that the element, in this case X, satisfies the defining property of the set T. So here's the defining property of the set T. And so I have to show that X is between 1 and 2. And how am I going to actually do this? I'm going to work forward. So let's work forward from the fact that X belongs to the set S. This is the statement A1. You chose X to be an element of S. Let's work forward from that. Because X belongs to the set S, it satisfies the defining property, namely X squared minus 3X plus 2 is less than or equal to 0. And now what I propose to do is algebra to go from A2 to B4. Help me with the algebra. What can I do here?
Factor.
Factor, good. X minus 2 times X minus 1 is less than or equal to 0. That's a new forward statement. Now look at what this is saying. This number, X minus 2, times this number, X minus 1, is less than or equal to 0. How can the product of two numbers be less than or equal to 0? One of them has to be negative and the other positive. So either X minus 2 is non-negative and X minus 1 is less than or equal to 0, or else x minus 2 is less than or equal to 0, and x minus 1 is greater than or equal to 0. One has to be positive and the other negative, or vice versa. All right, let's look at the top one here. X minus 2 non-negative. That means x has to be bigger than or equal to 2, and x has to be less than or equal to 1. How many numbers do you know that are bigger than 2 and less than 1 at the same time? Do you know of any? I hope not. So this cannot happen. This cannot happen. So that means this must happen. And what does it mean to say that x minus 2 is less than or equal to 0? X is less than or equal to 2, and x is greater than or equal to 1. And that is precisely B4. This completes the choose method. That's the model proof. Here's the model proof. And that completes the entire proof that S is a subset of T. Any questions on how this worked?
Would you recommend changing notation?
Would I recommend changing notation? In the beginning, yes, to distinguish between the chosen object and the general object. After you do this for a while, there's no need to do that unless you particularly want to. Notation is a personal choice. You're welcome to do it at any time, choose different symbols. You're welcome to choose the same symbol. Just keep in mind that the chosen object is different from the general for all object. Good. Okay, we still have to show that T is a subset of S in order to get the two sets to be equal. Here's a condensed proof that T is a subset of S. And what I'd like you to do is take a few minutes to read this proof on your own. Okay, now that you've had a chance to read this proof, what we want to do is learn to understand this proof as a sequence of applications of the proof techniques. Because as you noticed, the author does not mention any proof techniques when they write these condensed proofs. Do you see, for example, the word choose method anywhere? No. Do you see the word forward backward anywhere? No. Do you see the key question written anywhere? No. All of that is done up here. So what you have to learn to do is read these condensed proofs and explain them to yourself as a sequence of applications of the proof techniques. And the key to doing that may involve your having to do some work as you read the proof. So what we're going to do right now is learn to interpret all of these sentences in the context of proof techniques. So first, let's identify the hypothesis and the conclusion from the proposition. So here's the hypothesis. S and T are the sets defined by S equals the set of real numbers x such that x squared minus 3x plus 2 is less than or equal to 0. And T is the set of real numbers x such that x is between 1 and 2. And what is the conclusion? What are we trying to show? T is a subset of S. Here is the first sentence that we want to interpret. To show that T is a subset of S, let T be an element of T. What proof technique is the author using? And when you cannot answer that directly, then you want to stop and say, well, what proof technique would you use to begin this proof?
Forward, backward?
Forward, backward. Why?
Because there is no defining.
There's no defining keywords in the conclusion or the hypothesis. Good. So if you were going to use the forward, backward method, let's start with the backward process. What is the key question that you would be asking here? How can I show that a set is a subset of another set? And hopefully that's exactly what the author did. And what's the answer to that? How can you show a set is a subset of another set?
All the elements in one set are in the other set.
And where did you get that from?
Definition?
Exactly. Let's use a definition to answer the key question. I told you this is very common, right? How can I show that a set, namely T, is a subset of another set, namely S? I must show, by definition, that for every element x in T, x is in S. If you were doing this proof, what would you do next and why?
Use the choose method?
Yes. Why use the choose method? What did you recognize?
A for all in the backward process?
A for all in the backward process. You have to show that for every object with a certain property something happens. That should exactly trigger you to think about using the choose method. Before we use the choose method here, let's identify the objects, the certain property, and the something that happens. What are the objects here? Elements x in the set T. What's the certain property? There is none, right? And the something that happens is x is an s. Now again, you have to remember how the choose method works. And I'll remind you, you have to choose an object with the certain property. So what should I choose here? Choose an element, and here I'm going to use a different symbol. That's my choice. Choose an element T and T. And notice that that is exactly what the author says right down here. Let x be an element of T. That word let, in this case, is indicating that the choose method is being used. So please notice what's involved in understanding this very first sentence. Buried in this first sentence is the forward-backward method and the key question, how can I show that a set is a subset of another set, for which the answer by definition is B1. Here, the author recognized the keywords for all in the backward process, decided to use the choose method, and accordingly chose an object with a certain property and says, let T be an element of T. Notice how much of the thinking process is hidden. Okay, let's go back to that choose method. You have to choose an element T and T, an object with a certain property, for which you must show that
The something happens.
the something happens, which means what in this case?
X is an element of S.
X is an element of S, but you have to do it for your chosen object.
T is an element of S.
T is an element of S. That becomes your new statement in the backward process. Here's what the author says in sentence S2. It will be shown that T is in S. Indeed, that's what has to be shown. These two sentences, S1 and S2, that's the choose method. Okay, so here's where we are. We chose an element T and T. We have to show that T is in S. Let's see what the author writes next. Since T is in the set T, T is between 1 and 2, and so this happens. Can somebody tell me where is this sentence coming from? What is the author doing in terms of our proof techniques?
He's defining what it means for an element to be in the set T.
That's correct, and in terms of our proof techniques, this is a
Forward step.
forward step. Exactly. The author is working forward from A1 by using the definition of what it means for T to be in the set T. And in fact, here's the set T. And so if T is in that set, T has to be between 1 and 2. And that's exactly what the author writes here. Okay? So presumably, the reason that the author is doing this is to get to B2. So let's ourselves ask a key question here. Look at B2. What's the key question? How can I show that
An element is contained in a set.
an element belongs to a set? And how do you show an element belongs to the set?
It satisfies the
Defining property, right? And so here's the set S. There's the defining property. So we have to show that T squared minus 3T plus 2 is less than or equal to 0. And what we propose to do is work forward from here to get to here. And in fact, it's quite easy to do. Here's where we are. We need to work forward from A2 to get to B3. And that's actually pretty easy to do, but let's read what the author writes. Thus, T is in S since T squared minus 3T plus 2 equals T minus 1 times T minus 2 is less than or equal to 0. Where does this come from? The author is using algebra to start with T squared minus 3T plus 2 and factors it. Now, what do you know about T minus 1? Greater than or equal to 0. What do you know about T minus 2? Greater than or equal to 0 times less than or equal to 0 is, and that's exactly what the author has written here. T squared minus 3T plus 2 equals T minus 1 times T minus 2 is less than or equal to 0. This is working forward from here by algebra. But now A3 and B3 are exactly the same, and so the proof is complete. Let's take a moment to summarize the choose method. So first of all, you should think about using the choose method when you encounter the keywords for all, for each, for any, for every in the backward process, in which case you have to show that for every object with a certain property, something happens. And when you see those keywords for all in the backward process, that's the time to think about using the choose method. How does the choose method work? First, you have to identify the objects, the certain property, and the something that happens. Keeping in mind that when you identify the object, be sure to include what kind of type it is, a real number belonging to a set S, whatever it is. And watch out because certain parts may be missing, like the certain property, and things may be out of order or implied. So be careful to identify the objects, the certain property, and the something that happens. Then, after you do that, choose an object with the certain property. Let's call it X. And that becomes a forward statement. When you choose a general object with a certain property, that becomes information you can work forward from. And what do you have to show for that chosen object? That the something happens, which becomes the new statement in the backward process. Then you fill in the details of that proof. That completes this lecture.